All right, so 3.4, zeros are polynomial functions. Zero is another word for roots. And if you're not used to seeing the word roots, solutions is another word for that. So zeros, solutions, roots all mean the same thing. So talking about solutions of polynomial functions. So I believe it was this class, yeah, I believe Deep had mentioned, you know, if you don't have any hints on solutions, how would you go about solving your equation? Well, this is how we would start it, looking at all of our possible rational zeros. So that's our rational zero theorem. What we would do is take plus or minus will be applied to each one of them. I'll show you what I mean in a second. But the factors of your constant over the factors of your leading coefficient. And that will give you all of your possible solutions. All right. That comes from this right here. If you were to solve your 2x plus 3 equals 0, you were to solve that. That 3 is your constant. The number that's not attached to your variable is your constant. Your leading coefficient is the number that's sitting in front of your highest, your variable with the highest exponent. So if I were to solve this, I would subtract 3 from both sides, divide by 2, and notice that my constant is over the leading coefficient. And so that's where this process comes into play. We're talking about all of our possible rational zeros. We take the factors of our constant and place it over the factors of our leading coefficient. All right, give you guys a chance to write that. All right. So next example, or the first example. First example is to list all possible rational zeros of 15x cubed plus 14x squared minus 3x minus 2. All right. So our constant is the 2. Our leading coefficient is the 15. And so that's what I wrote right here. Constant is 2, leading coefficient is 15. Our factors of 2 is just 1 times 2. Factors of 15, 1 times 15, 3 times 5. All right. So now what we're going to do, once we've established our constant and the factors, leading coefficient and factors, we'll take each one of our factors of our 2, the constant, and place it over each one of the factors of the 15. So that's 1 over 1, 1 over 15, 1 over 3, 1 over 5, 2 over 1, 2 over 15, 2 over 3, and 2 over 5. All right. And that's going to be plus or minus each one. I just didn't repeat the plus or minus writing. So simplify your terms. 1 over 1 is just 1, 2 over 1 is just 2. And we have 16 possible rational zeros. All right. So we have 16 possible solutions to help us get started on trying to find the actual solutions of that equation. And we, of course, will do that process before we close out today. All right, any questions before we do another one?
How did you
Just hold on a second. I just got to copy this.
how did you get to 16?
Plus or minus Each one.
Okay.
Mm-hmm. So it's plus or minus 1, plus or minus 1 over 15, and all the way down the line. All right. Scroll up a little bit. Looking at the next one. 4x to the fifth.
There's a comment in the chat.
Oh, okay. Let's see what you got going on. You wouldn't do, the 15 would be in your denominator. So remember, it's always your constant over the leading coefficient. So you put 1 over 1, 1 over 15, 1 over 3, 1 over 5, 2 over 1, 2 over 15, 2 over 3, 2 over 5. Remember, if it's your leading coefficient, what was that? Leading coefficient, that means, let's say if we have 15x, hold on 1 second. So if you have 15x minus 1 equal to 0, if I were to solve this, I would add 1 to both sides. That's 15x equal to 1. Divide by 15, that's x equal to 1 over 15. See, the 15 would never be in your numerator because it's your leading coefficient. That's what you would divide. So that's why the 15 would be in your denominator. So that's why 15 couldn't be, because 15 is our leading coefficient. Now, if 15 was the constant, in other words, if I had x, not x equal, x plus 15 equal to 0, then I could subtract 15 to both sides, and it would be x equal to negative 15. But 15 would have to be here and not here. So it's all about what is your constant and what is your leading coefficient. All right. So let's try it again. We have 4x to the fifth. No, not a problem. Plus 12x to the fourth minus x minus 6. So we see that our constant is 6. Leading coefficient is 4. So we look at the factors.
I have a question. So if we have a negative for the constant, it's still like positive, or?
Yeah, all we're doing is looking at the numbers, because when we look at our solution set, we're gonna look at plus or minus anyway.
Okay.
Yep.
Thank you.
Yep, not a problem. Not a problem. Good question. So let me put an equal sign right here. So yep, so our constant is 6, leading coefficient is 4, factors of 6, 1 times 6, 2 times 3, factors of 4, 1 times 4, 2 times 2. And I'll go ahead and do it. So we'll just take our factors of 6, I'll go with blue. Take your factors of 6 and place them over the factors of 4. So you have 1 over 1, 1 over 4, 1 over 2. And notice we have 2 that's being repeated. You don't have to repeat it because 2 is 2, no matter how many different ways you write it. And so we'll do 6 over 1, 6 over 4, 6 over 2, 2 over 1, 2 over 4, 2 over 2, and then 3 over 1, 3 over 4, 3 over 2. So that's your initial list. In a second, we're going to reduce, and we don't write any repeated values, not necessary. But that's our initial list. You place the numbers, the factors of your constant over the factors of the leading coefficient. Everybody okay? All right, so reduce or simplify your fractions. And we see that 2 over 4 is the same thing as 1 over 2. So, we already have that right here. 2 over 2 is the same thing as 1. We have that right here. 3 over 1, 6 over 2. And then 3 over 2 is the same thing as 6 over 4. So we don't write them twice. Simplify and do not write your repeated solutions. And here we have I mean, we have here 1, 2, 3, 4, 5, 6, 7, 8. What, 16 possible solutions again? They call them zeros. I'll stick with zeros.
Professor Tucker,
Yep.
what happened over here at 3/1? Oh, that just became a 3 right here, right?
Mm-hmm.
And we don't rewrite them.
Right. Because we had 6/2, which was 3. So
Yeah.
I don't need to write 6/2 and 3/1. Right.
Okay, so just 1, 3 is okay. Don't rewrite them.
Right. Mm-hmm. All right, somebody else in the chat. You don't, well, not multiplying by 2 necessarily. Well, it's being multiplied by 2 because you're considering plus and minus for each one of the scenarios. So there's plus or minus 1, plus or minus 1/4, plus or minus 1/2. So I don't want you to just say, you're multiplying by 2 just for the sake of multiplying by 2, but you're multiplying it by 2 because each one of them represent 2 possible outcomes, the plus or minus of that. All right. Yep. Cool. Nice. All right. Any problems before we do it again, but actually take it to the next step and actually find our actual solutions? All right.
Professor Tucker,
Yes, sir.
we multiply the denominators.
No. Why you say that?
Like I see 1, then 1/4, 1/2, 6/1, 6/2.
Mm-hmm.
4 times 2 is 8. 4 times 2 is 8. I'm
Okay.
trying to figure out
So what are you trying to do? Just wanna.
how you getting 16.
No, that's what one of your classmates asked in the chat. Oh no, I still have my wrist up. Okay. Multiply this list by 2. We had 8 values here. So one of your classmates asked, do we just multiply that list by 2? Because we have 8 values. And the reason why you're doing that is because each one of them is plus or minus.
And each fraction, you got to reduce it.
Yes. Yes, that's how we went from here to here because we reduced all of our fractions.
And we add denominators.
No. We're not doing that. We just have individual solutions. Why are you saying that we add denominators?
I'm trying to figure out how you got 16.
You talking about this?
Yes.
Yeah, we got 1, 2, 3, 4, 5, 6, 7, 8. 8 times 2 is 16.
Okay.
I think you're going a little too deep on it. I just said, so that's just 16 possible solutions. So, plus or minus 1, plus or minus 1/4, plus or minus 1/2, plus or minus, like plus or minus each one of these solutions right here. You see what I mean?
Okay.
Yeah. Yeah, the plus or minus, I just didn't write it each time, but that plus or minus extends to each one of those solutions.
Okay. Thank you, Professor.
Not a problem. Just want to make sure you're straight though before we roll on. All right. So you good to go now?
I'm good.
Okay, cool. All right. So the next one, we have x cubed plus 7x squared plus 11x minus 3. Notice our highest degree of x is 3, so we should be looking to have 3 solutions. Our constant, just like before, is the number that is not attached to any variable at all. That's going to be our 3. And then our leading coefficient here, which is good for us, that's just 1. So we have our factors of 3, which is 1 times 3, factors of 1, 1 times 1. And we put 1 times 3, the 1 and the 3 over the 1. So we have 1 over 1 and then 3 over 1. And so I'll stop right here, make sure we're good. So we only have 4 possible solutions.
Professor Tucker,
Mm-hmm.
for this one, we don't have to do the constant, right? We don't have to do the constant 3 over, oh no, because we already did it, right?
Yeah, we did do it. Yeah.
You're writing it. I got you. You just skipped a couple steps right there. I got you.
Oh, yeah. Let me see. No, I did it pretty much. Yeah, I did them
You
all.
skipped the steps, but you just didn't write them. You just made it simpler.
Well, it's just that this had less work If you
Yeah,
look at these we had this, and then here, all we have is just the 1 times 3 and 1 times 1.
I
So
got it.
yeah, it looks shorter, but it's really the same steps. Yeah, this was a lot shorter because of our options. Yeah. All right. So we have these 4 possible solutions. We have -1, +1, -3, and +3. So we're going to use synthetic division to see which one, or which 2, or which 3, if all 3 of them are solutions or not. If, you know, or in that list, I should say, then we will get 0 as a remainder. Remember we talked about last class, the zero factor theorem, remainder theorem, not the zero factor theorem, the remainder theorem, and the remainder theorem and the factor theorem, those 2 different ones, that if we get 0 as a remainder, then that lets us know we have a solution. So we do synthetic division with our first one, which is 1. Put 1 in the box. We have 1, 7, 11, and 3, -3 from our coefficients right here. And so you bring down 1. 1 times 1. Oh, didn't mean to do that. I'll just erase it. 1 times 1 is 1. 7 plus 1 is 8. 1 times 8 is 8. 11 plus 8 is 19. 1 times 19 is 19. -3 plus 19 is 16. So since we got a 16 right there, that is not a solution. We need 0 to be right there in order for it to be a solution. Then we do -1. Bring down 1. -1 times 1 is -1. 7 plus -1 is 6. -1 times 6, -6. 11 plus -6 is 5. -1 plus -5 is -5. Add -3 and -5 together, and we get -8. Once again, that's not a solution. So we follow the same procedure for the next 2. And we'll see for +3, we end up getting 120. So that doesn't work for us. But then for that last one, we get 0 as our remainder. So that lets us know that that is a solution. I'll give you a chance to write that down for those who are doing so. So it ended up being the last one that we had, ended up being a solution. All right, somebody in the chat. yeah, it is a little bit of work. Oh, the other way to do it, don't forget I didn't mention this to the last class, the other way to do it. So it just depends on if my math lab asks for that type of info, something like that. But anyway, the other way is to plug the values into f of x. So remember, that's the remainder theorem. So remainder theorem, you plug into f of x, get 0. Should give you out the same thing. So it just depends on how you want to do it. But I knew that synthetic division was one way we need to reemphasize to make sure everybody's okay with that synthetic division process.
So what did you do with, I kind of got lost. You know when the top it says 1, 7, 11, -3, those are the
coefficients.
Yeah. How do
Mhm.
you get the -1, -6, -5?
Right here. Remember our values, our possible solutions. When we take 1, 3 and place it over 1 and 1. So basically we did this process, this right here.
Okay.
Yeah, so those are our possible solutions. So 3 was our constant, and then 1 was our leading coefficient. So we took the factors of 1 and 3, which is 1 and 3, and placed them over 1. So 1 over 1 and then 3 over 1. So that it just gave us 4 solutions. And so those were the 4 solutions that we tried. 1, -1, 3, and -3.
So when you're plugging them in, um you're adding them.
When you say plug it, you talking about when I plug it in right here?
Yeah.
Okay. So what happens is when you're doing the synthetic division process, the first move is to bring this first term straight down. So that's why 1 is right here. Then you multiply what's in this box to this number. And then you take that up here. That's how you got that 1. That's how you get this one. Whatever's in the box times whatever's down here. And that's how you get that one. Add these together. 7 plus 1 gives me 8. Then 1, this one right here times 8 gives me this. Add those together, then 1 times 19 gives me this. And then add -3 and 19, that gives me 16.
Oh, okay. Thank you.
Okay, not a problem. All right, any other questions before we look to finish this off? Okay, so we have x4 -1. Remember, you start off with one exponent less than what you originally had. Remember, we had x cubed. So now we have 1x squared plus 4x minus 1. We broke down the function to x squared plus 4x minus 1. Cannot factor this out. So we use the quadratic formula. That means A is 1, B is 4, C is -1. And we take those and plug it into the formula. So that's -4 plus or minus 4 squared minus 4 times 1 times -1. All over 2 times 1. All right, so we simplify what's under the radical. 16 plus 4, which will give us 20. And we can break down that 20. 4 times 5, square root of 4 is 2, so that's 2 square root of 5. Or you can reduce further, taking that 2 into each term. So 4 divided by 2 is 2, and then those 2's cancel, leaving me with just square root of 5. And those will be my other 2 solutions. So here are all 3 of our solutions right here. -3, -2 plus square root of 5, and -2 minus square root of 5. All right. Questions on that? It should be okay. All right. Complex conjugate theorem. If a plus bi is a solution of f of x, then a minus bi is also a solution. So your imaginaries don't travel alone if they are solutions. So your conjugate just means you take the middle sign, your imaginary, the sign of your imaginary, and use the opposite. So conjugate's 4 plus 5i, 4 minus 5i, negative 2 plus 7i, then negative 2 minus 7i. Then we have negative 8i and positive 8i. So once again, your conjugate is just going to be the imaginary sign, the opposite sign of your imaginary. The real stays the same, it's just the opposite sign of your imaginary. All right. We're still holding on to the complex conjugate theorem. All right. So this example, or the next two examples, I'm going to focus on that same process. It tells us here to find a fourth degree polynomial. Fourth degree means 4 solutions. Highest exponent of our polynomial is 4. With coefficients, real coefficients, that has negative 2, 2, and I as zeros, such that when you plug in 3, you get out negative 150. So f of 3 is equal to negative 150. So what they do here, or what they have done here, so what I have in the green, they give us the solutions, and they want to know what function will produce the solutions. All right. So they give us these 3 solutions, negative 2, positive 2, and I. And they asking us what function will give us these 3 solutions. And also when I plug in 3 into it, I have an initial condition that when I plug in 3, I get out negative 150. All right. So remember, it's a 4th degree polynomial. Gives us, that means we need to have 4 solutions, but they only gave us 3 solutions. But don't forget, we just finished talking about the complex conjugate theorem. So if we have complex numbers, then we know we have at least 2 solutions. And that's where negative I comes into play as our 4th solution. Because we have I as a solution, that means negative I is also the solution.
There's a negative I.
Mm-hmm. Yep. Just like there's negative 5I, you know.
Yeah. Oh, I is imaginary numbers.
Yeah, but it can be positive or negative. Yep. You know, just like we could have 7 minus 2I or 7 plus 2I or
You
negative
can't do
7.
nothing with it.
Say again?
You can't do anything with it because it's imaginary.
But if you
They're
have
two different.
but if you have an imagination, right? Oh, I lost you. So so don't forget, always keep in mind that we're working in reverse when we talk about these type of problems. We have the solutions and we want to create this function that will produce these solutions. But in order for me to get x equal to negative 2 as a solution, the first thing I had to have was x plus 2. Remember, you would subtract 2 from both sides, then my solution would be negative 2. Same thing with the other 3 solutions. I have to have the opposite in order for me to get that when I add or subtract it from both sides of the equation. So when I go to set it up, let me erase this bottom one just to be clear on what I'm talking about. I'll put it back in a second. Notice how we set this up. I do x minus whatever my solution is right here. So x minus negative 2, x minus 2, x minus I, and x minus negative I. So this set it up this way. This will really help us in the next one. But you want to keep the same flow, the same process, the same procedure. So you do x minus whatever your solutions are. And that will ensure you have the opposites when you go to solve.
So do the conjugate of what you see.
Say that again.
Do the conjugate of what you see.
I was, as far as terminology go, you would say the opposite. You still stick with the opposite mathematically. You know.
Okay.
Yeah, you'll stay that. Now I understand where you're going with it, but just because of mathematically opposite always just means the opposite sign. Conjugate adds a little more detail to something, so I would say opposite. Yeah.
Okay. Thank you, Professor.
Not a problem. Also take note that I put a right here in front of our new function that we're creating, because it's possible that we're going to have a number that we're going to need a to b in order to produce that initial condition. So we'll talk about that as we progress forward. But what you don't want to do is use x or y, because that's, y is equal to f of x, and we already have x involved. So normally we just use a right there to represent the possible number that we will place there to help us to fulfill our initial condition. All right, so we have our setup. Once again, we're doing that so that we can have the opposite numbers when we get our solutions. And give me my stuff back. There we go. So now go ahead and use those opposite signs. That'll be x plus 2, x minus 2, x minus I, and x plus I. Now what you want to do is multiply these together and multiply these two together, doing your binomial distribution. So foiling that out gives us x squared minus 2x plus 2x minus 4. X squared plus ix minus ix minus I squared. All right, combine your like terms. When you do that, you see that your middle terms will cancel. So that's why I say it was in your best interest to multiply these two together and then these two together, especially when it comes to those conjugates. And then that'll leave us with this right here, x squared minus 4, x squared minus negative 1. Don't forget I squared reduces down to negative 1. Distribute x squared minus 4 into x squared plus 1. That gives us this. X to the fourth plus x squared minus 4x squared minus 4. Combine your like terms in the middle. That'll give us minus 3x squared. All right, so you see all this is algebra. Doing a lot of distribution. Just got to make sure you pay attention to your signs. Keep track of your terms. Make sure you don't lose any. All right. So now we have to bring in that initial condition. F of 3 is equal to negative 150. So when I plug 3 into this function, I'm supposed to get out negative 150. That's what I did right here. So plug in 3, excuse me. Every 3 to the fourth minus 3 squared, minus 3 times 3 squared minus 4. 3 to the fourth, 81. 3 squared is 9. That'll be 81 minus 27 minus 4. which ends up giving me 50. $50A equal to negative 150. Divide by 50, and A is equal to negative 3. All right, any questions before we finish this one off? All right, so A is equal to negative 3. Go ahead and plug that in for A. Mm-hmm.
-3, but the function has a 3 there.
No, this 3 has nothing to do with this negative 3.
Okay.
Yeah, those are two different things. It just so happened that A was equal to negative 3, but they have nothing to do with each other. If we could have solved down there and got A equal to 7, and that still would have been 3 right there. Those two had nothing to do with each other. All right, so you plug in negative 3, go ahead and distribute it to simplify your function. And we have negative 3x to the 4th plus 9x squared plus 12. All right. Questions before we try it again? All right.
I got it. So basically, once you get your function, you take that -3 and put it on the outside, then multiply it to your function.
Mm-hmm.
Oh, man. Okay.
Yes, sir. All right, so the next one, third degree polynomial, same direction, is just that this time we have a third degree polynomial. So that means we should have 3 solutions. All right. They give us -5. Let me make it a little bigger. No, I don't want it that big. -5 and 4 plus 3i are zeros. And then when I plug in 2, I get out 91. All right, so they give us 2, -5 and 4 plus 3i. But they assume that you know that since you see 4 plus 3i, that means 4 minus 3i is also a solution. That's that complex conjugate theorem. All right. Erase some stuff. All right, so now you use the opposite signs for each one of those solutions. So notice I have x minus -5, x minus 4 plus 3i. Notice I had a parenthesis around that. That minus sign needs to be applied to each term. Then x minus 4 minus 3i. All right. Go ahead and distribute those negatives. And then we know negative to negative turns positive for that 5. That'll give us this as a result. X plus 5, x minus 4 minus 3i, x minus 4 plus 3i. And like I mentioned last time, we're going to go ahead and multiply the terms that have, or the parentheses, the quantities that have the conjugates in them first, so things can cancel out for us. and it'd be less work on the back end. So I'll distribute x into the other parentheses, distribute -4 into the other parentheses, and then distribute -3i into the other parentheses. Also, notice we have that a still sitting out here in front. Remember I told you that's what we need to do, put a out there, just in case we need to multiply like last time. A ended up being -3. So that means we needed that -3 to be a part of the function in order for us to get -150 when we plugged in +3. Okay. So our result of our trinomials, multiplying those two together, we have x squared minus 4x plus 3xi minus 4x plus 16 minus 12i minus xi plus 12i minus 9i squared. So that will enable some things to cancel out for us. Why is my stuff not coming back? There we go. So the 3xi and the -3xi will cancel. 12i and the -12i will cancel. And then also -4x and +4x will come together to give us -8x. All right. Don't forget that I squared is -1. So we have a +9 right here. So +9 plus 16 will give us that 25 right here, which gives us, now we have this function, x plus 5 times x squared minus 8x plus 25. Go ahead and distribute. X times x squared will be x cubed, and you see -8x squared plus 25x. Distribute the 5x squared minus 40x plus 125. Combine your like terms. -8x squared plus 5x squared gives you -3x squared. Then 25x minus 40x give you -15x. And so this is our most simplified expression up to this point, but we still need to figure out if a will represent a number for us that will matter to our function. All right. So now we have the initial condition that when we plug in 2, we should get out 91. So we plug in 2 cubed minus 2 times 2 squared minus 15 times 2 plus 125 is equal to 91. 2 cubed is 8, 2 squared is 4. 8 minus 12 minus 30 plus 125 ends up giving us 91. So now solving for a, divide 91 to both sides. A is equal to 1. Once you found out what a is, plug it in. And you know 1 times anything is itself, so 1 or a didn't really, wasn't a real factor in this case because it ended up being 1. So our final function is going to be x cubed minus 3x squared minus 15x plus 125. All right, questions? Any questions? Everybody good? All right. So as always, try the stuff out, see if you have any issues, and then we'll, bring it to class or shoot it to me in an email, and we'll go from there. All right, we'll start 3.5 since we have a little bit of time. Start 3.5. 3.5 content isn't that in depth as long as you follow the steps. So we're looking at rational functions and their graphs. So it says something about the last note. What is it that you see you need? All right, so you see, do you see it? Make sure you're getting it. All right, not a problem, not a problem. All right, so that thank you mean that you're good to go? All right, sounds good. All right, so looking at asymptotes, these are places where the function is undefined or does not exist, or in other words, places where the graph does not cross. All right, first type we've already done before, just didn't call them asymptotes. We have three types. We have vertical asymptotes, horizontal asymptotes, and slant asymptotes. Slant asymptotes are also called oblique. Everybody good? Don't want to go too fast. All right. So first one, vertical asymptotes. So where the denominator is equal to 0. So you would simplify as much as possible. And then set the denominator equal to 0 to solve. Which is something that we've done before. So yep, it's the same thing. Holding on to these. All right, so find vertical asymptotes, if any. So notice the first one is x over x squared minus 9. So it can't be reduced any. So we just set that denominator equal to 0, x squared minus 9. Excuse me. So when you look at your graph, you were to graph this, you should have these imaginary, lines. You may not see them, but you can see the graph would not cross those lines. And those would be your vertical asymptotes. So you would have two. You have one at x equal to -3 and one equal to at x equal to 3. So your graph would curve according to those vertical asymptotes. And your graph would never cross those lines. All right, any questions on that? Next one, g of x. We have x plus 3 over x squared minus 9. Now this one we can simplify. Notice we will look at x plus 3 over x plus 3 times x minus 3. Those x plus 3's will cancel and leave us with just 1 over x minus 3. Now, because the function originally had x plus 3 in the denominator, we can't just ignore it. But we notice that it did cancel out. Because it cancels out, it will not produce a vertical asymptote, but it will produce a restricted value. That's what I have right here in green. In other words, you know, when we've had graphs in the past, it would be a line with like maybe an open circle. So this would produce an open circle at that spot. So what's left is going to give you a vertical asymptote. The one that canceled out gives you a restricted value. And so that's what we have here, restricted value at x equal to -3 when you solve it for x. And x equal to 3 gives you a vertical asymptote. All right. Questions on that? One more scenario. If we
Mr.
had,
Tucker,
yes.
basically doing rise over run to get our points.
No, we're not doing it. No, we're going too deep. All we're doing is
Okay.
just taking the denominator, setting it equal to 0. And
All right. Thanks.
solving it for x. Yeah, you don't even want to go there with it.
All right.
Because then you're talking about incorporating, using your slope and everything. So you don't want to go there for this anyway. Yeah.
Thank you.
Yeah, no problem. So the next one, we have x squared plus 9. We cannot factor that. So if we go ahead and set it equal to 0, Mr. Cooley mentioned, you know, we have imaginary number here. Since it's imaginary, that means it does not exist for us, so there is no vertical asymptote. All right, questions on those three before we look at horizontal asymptotes? All right, for your horizontal asymptote, the first thing they do is set us up with, we're gonna let n be the degree of the numerator, m be the degree of the denominator. So in other words, we're talking about the highest exponent in your numerator is the degree of your numerator. Highest exponent in your denominator is the degree of your denominator. All right. Once again, n is the highest exponent in your numerator. M is the highest exponent in your denominator. So they're saying if n is less than m, your horizontal asymptote is y equal to 0. Also take note that when we're dealing with our vertical asymptotes, we use x equal to, with our horizontal asymptote is y equal. Okay. If your exponents are the same, you take the leading coefficient of each, take the leading coefficient of the numerator, place it over the leading coefficient of your denominator. That will be your horizontal asymptote. And then if n is greater than m, the numerator's exponent is greater than the denominator's exponent, there is no horizontal asymptote, and we will just go, we will go to slant asymptotes. That will let us know we have a slant asymptote. All right, let's roll up. So here we want to find the horizontal asymptotes, if there is one, or if there are any. So to give us f of x over 2x squared, f of x is equal to 4x over 2x squared plus 1. So when we look at our exponents, our highest exponents of each, see that 1 is in the numerator, 2 is in the denominator for our exponents. Talking about our exponents. Remember, that's what's going to dictate what we do first, or how we handle establishing what a horizontal asymptote is. The exponent or the degree of our numerator is 1, degree of our denominator is 2. So since the degree of my numerator is less than the degree of my denominator, our horizontal asymptote, let me make sure I didn't do anything. Okay, take it back. All right, there we go. So horizontal asymptote y is equal to 0. So no calculation, just observation. If the degree of, or the exponent of my numerator, highest exponent of my numerator is less than the highest exponent of my denominator, my horizontal asymptote is 0. What does the end of 3 say? We will go to slant asymptotes. Slant asymptotes. Remember, that's our third one. Third type of asymptote. So probably go back and write that better next time. All right, is everybody okay? All right, so the next one, 4x squared over 2x squared plus 1. Notice our exponents are the same. So we take the 4 and 2 for the numerator and denominator. 4 over 2 is going to reduce down to 2. So my horizontal asymptote is y equal to 2. And then the last one, 3 is greater than 2 for our exponents. If your numerator's exponent is greater than your denominator's exponent, then there is no horizontal asymptote. Questions, questions, questions. Everybody good, everybody straight. We got a few minutes left. We might as well finish off this last one. Process is just division. So we've done that before. Is anybody still copying before I scroll up? All right. So your slant asymptote exists when your numerator's exponent or numerator's highest exponent is greater than your denominator's highest exponent. So that's when you have your slant asymptote. You'll use long division or synthetic division to find it. It's up to you which one you want to use. Remember, synthetic division has those rules in place. So we'll build this form. Whatever your quotient is, that will be your slant asymptote. So your remainder, I still have my eraser on. So your remainder is not a part of your slant asymptote. Also take note that y is y equals for your slant asymptote, y equals for your horizontal asymptote, but x equals for your vertical asymptote. All right. So find the slant asymptote. If we have x squared minus 4x minus 5 over x minus 3, like I said, this is the process that we've used already, synthetic division. Once again, what allows us to do our slant asymptote is the fact that we have x squared here, x to the first power here. In other words, 2 is greater than 1. Exponent of my numerator is greater than my exponent of my denominator. I decided to use synthetic division. Opposite sign from that 3. So that's why I have positive 3. Then I use all my coefficients, 1, negative 4, negative 5. Bring down 1. 3 times 1 is 3. Negative 4 plus 3 is 1. 3 times negative 1 is negative 3. Negative 5 plus negative 3 is negative 8. And so this is the result here. But my slant asymptote is just the x minus 1. Any problems, any questions before we look at this last one? All right, last one is similar. We have x squared plus 1 over x minus 1. I ended up having a missing term. Don't forget, if there's a missing term, then we are to add 0 as a placeholder. Use that opposite sign here in my box. Coefficients from this, 1, 0, 1. Bring down 1. 1 times 1 is 1. Add your 0. Get 1. 1 times 1, once again, is 1 again. And then 1 plus 1 gives me just 2 as a remainder. So the result is all of this, x plus 1 plus 2 over x minus 1. But the slant asymptote is just this part right here, the quotient, which is x plus 1. Questions, questions, questions. All right. So, try the stuff out. See if you get stuck. If you have any questions, make sure you bring it to my attention so we can knock them out. Make sure your questions are answered. This is section 3, 6. A couple more sections left. So we'll be looking to review after that, having that open session for you to ask whatever questions you want to ask, and we'll talk about how we're going to move forward. Questions, concerns, comments before we close? All right, good, everybody straight.
Since we didn't have a proctored test for the last one, would it be for this one?
This is chapter 3. It's either going to be 3 or 4. Haven't decided yet. But you'll have enough time. I'll most definitely give you enough time to prepare for it. Before I tell you, So if I won't say it's proctored test next class, like I won't do you like that. So you guys will have ample amount of time to prepare for the proctored test.
Okay, because they give me anxiety, so I want to prepare before I do it.
Right, most definitely. And then if we do a proctored test, I won't take your notes from you. So I will give you the opportunity to be able to do that. But what you want to do is, shape your notes according to, the test. You don't want to have your notes all over the place and you wasting your time. So, we'll talk about that, as we progress forward, though.
Okay, thank you.
Mm-hmm, no problem.
She ain't alone with a test anxiety thing.
Man, I knew you were coming.
I'm glad she waited to the end of class to mention the test, because you mentioned the test at the beginning of class. That's all I'm thinking about is tests. So
it's all good, sir. So with that being said, like I said, we'll talk about the test, when we get closer to it and how we're going to operate with it and administer it, outside of that though, relax. No test is coming up tomorrow or next class. So I will see you guys next class. You have a good one. And take care.
Hey, I'll be hitting you up via email because this was a hard one today.
Oh man, you
yeah, me too. All right, boss. Thank you.
All right.
Hey, I'll put the video on. My head white as snow. You just made it whiter. For real. Thanks, Professor Tucker. You killing me sooner.
All right, not a problem, sir. I do what I can.
You have a good day, Professor.
You do the same. You do the same.